Okay, so now we are going to come back to the topic of random variables. But we are now going to see what how these random variables behave when they are defined on continuous or uncountable sample space. Or let us say on or for the case of uncountable omega, such as omega itself being a subset of R, that is a real line. So, this is the simplest such uncountable sample space that we have right. Okay. So, to define a random variable we basically need a functional mapping between every sample point and the real line itself. So, let us review the definition of a random variable. If you review the definition of a random variable, what is it? Well, let us use RV instead of saying random variable all the time, right. So, a random variable x is basically a mapping between the sample space and its range space, that is set of values that x takes, which is a subset of the real line. So, if this omega x is countable, which is what was the situation in all the earlier examples, right, then we called x a discrete random variable, right. So, earlier we had the case of omega x countable, which is identical to the case of discrete random variable. In other words, x can take only a countable number of values such as 0, 1, 2, 3, whatever. We have seen enough examples of that. But now I am going to move on to the situation where omega x is uncountable, which is certainly possible when the underlying space is a portion of the real line, right. So, omega x is uncountable means that you are basically dealing with a fundamentally different situation than a discrete random variable. So, but now, right. So, let me write here, now your omega x is uncountable. The set of values that x can take is basically not countable, and therefore, we need to deal with this situation carefully. Simplest example, as I said, is the case of the sample space itself being some portion of the real line, again a spinning pointer. This example comes up a lot in our study of random variables because it is such a simple but very often commonly encountered experiment where you spin a pointer and it comes to rest at the pointer comes to rest at any arbitrary position on the unit circle. The radius of the pointer is some let us say some number, could be normally taken to be unity, does not matter, right, and the pointer comes to rest at any point on the circle, and the angle that it makes, let us call this angle as omega. The angle that it makes with the positive x axis or some predefined axis is defined to be the output of the experiment. And the collection of all these angles is this set, the continuous or the uncountable set capital omega. So, for the capital omega, for the spinning pointer case, capital omega is basically the set of all real numbers between 0 and 2 pi, and for mathematical consistency we will say that 2 pi is basically the same as 0. So, we will use the not included notation for 2 pi, but includes 0, it is just for just convention. So, we spin the pointer and it comes to rest at any angle, right. The angle can be here in the first quadrant or second or third or fourth, basically it can be any angle between 0 and 360 degrees, right, or 0 and 2 pi in radians. Okay. So for this spinning pointer, right, we have defined the omega, but we have not defined the random variable x. So now the simplest definition of x, of random variable x in such situations is to take x to be the output of the experiment itself. This is a very useful important identity mapping which essentially says that the angle at which the pointer comes to rest is the value of taken by the random variable directly. So, there is no processing of that angle, the angle is directly assigned, right, to the value of the random variable. Okay. So, what is in this case, whenever you take x of omega equal to omega, then automatically the set of values taken by x is basically equal to the sample space itself, which is obviously uncountable whenever you are talking of any interval of the real line. So, and it need not be necessarily only spinning pointer. I could have a linear experiment where I could be measuring the distance from some origin, and that could be measured in an uncountable fashion, right, instead of in a discrete manner, right. And if I define this x of omega to be omega, then right, automatically the set of values taken by x becomes the same as the sample space itself. Okay. So now, right, earlier we used the concept of probability mass function to assign probabilities to x, but now we cannot do that because x takes an uncountable number of values, and so we have to use the earlier the concept of CDF and PDF that we did in the earlier lectures, and we have to propagate them or move them to this setting or to this case of this x. But the important thing that we should realize is that a discrete space such as tossing of a die or putting balls into bins, those discrete examples cannot support, or discrete sample spaces cannot support continuous random variables, right. So a discrete sample space can only support a discrete random variable, or right, a discrete they can only support, in other words, you cannot define continuous random variables with uncountable omega x for discrete spaces. So, if you want to define a continuous random variable whose range is infinity, whose set of values that it takes is not infinite, uncountable, then you must have a finer or a more continuous sample space, and that is and the simplest starting point for such spaces is where the sample space, the set of values that are possible in the experiment here is some portion of the real line. Then in that case, if you are starting with this, then you can automatically define the identity mapping itself as the most basic random variable of that experiment, and then this x is obviously a continuous random variable. Notice, however, that this is not the only way that continuous random variables arise. There are of course many more complicated ways to define continuous random variables. For example, if omega is bigger than r, let us say it is some portion of the plane or it is a portion of 3D space. Okay. So, omega can be bigger than r. R is, when I say r without any superscript, means it means a real line, right, and r squared means plane. So, omega can be some subset of the plane. So, this situation where omega is some portion of the plane is the classical setting for the darts experiment. The most important example here being darts. What does a darts experiment do? select some portion of the plane as a target, then throw a dart at it from a distance, and because of the physics of the problem, the dart can land anywhere inside the target area, and therefore the all points in the target area become sample points of the experiment, and again the number of such points is uncountable, and therefore you can easily define continuous random variables for such an experiment, right. But now let's just take the case of let's not specify darts all the time. We will just take the more general setting of omega being some subset of r square for in some way. I mean, you could drop an object blindfolded onto a plane on the floor or something. You can do this in any number of ways, not just darts. Okay. Anyway, so let us say that omega, the sample space of the experiment omega is some portion of r square, which means basically that each sample point omega has two components. That is, each outcome of the experiment sample point is basically composed of an x coordinate and a y coordinate, provided you define the axis, or once you define the axis, which we have presumed that we have done by at the start of the experiment. So there is an x coordinate to the point of the sample point and a y coordinate, and together they define the outcome of the experiment. Okay, and so both of these now are continuous numbers, as opposed to here where you have only one number output by the experiment. So here that you get two numbers, omega x and omega y, and therefore we can define by extension of this idea, so we can define two random variables here, x of omega as omega x small x and y of omega as omega y. So this basically gives you two different random variables, assuming that there is some degree of freedom in that omega y x and omega y can sort of vary independently of each other, which is true for example in the darts case, right. I mean, there is no, if you pick this as the x and y axis, you throw it here, throw it here, throw it here, throw it here, right. Obviously there are 2 degrees of freedom, and the values taken by omega x do not tell you anything about the value of omega y in a particular trial. Okay, so anyway, so we have, in such cases it's clearly it's easy to see that you can define two random variables and both of them will be continuous. And both random variables specify this fundamental property of all random variables, namely that they are mappings from the sample space, to some portion of the real line. So if you have, for example, a more abstract setting where this could be some k dimensional subspace, space of R, some subset of R, I am saying that it could be R power k, for example, then you could have k components, right. So each of those components would be a different random variable, x1 to xk, or you could take the maximum of the k components. So that would be again a single random variable with uncountable sample space, because the maximum itself would be you could not count the number of values taken by the maximum, it's again uncountable, and so on and so forth. So there are many ways in which continuous random variables can arise in practice, and all of them are important in engineering. Most of them are important in engineering, so we have to take some time to understand and appreciate how they why they arise, and why it makes so much engineering sense to go through this exercise of defining them, because precise definition of a random variable is very important in many engineering problems. Okay, so but unfortunately we do not have the time now to go deep into examples, so let me keep going with the mathematical consequence of having continuous random variables, and later on, maybe if time permits, we can look at examples.